Alright, welcome back. Now, you know the atmosphere, you're all survivors of ATSEVS533, and so you know that the atmosphere is divided up into different layers. The layer closest to the ground is the so-called troposphere, and the next layer up from there is so-called stratosphere. After that, the layers of the atmosphere, there's so little air in them, they're not relevant to what we're discussing. Well, it turns out there's water vapor in the troposphere, and there's water vapor in the stratosphere. I wonder if they both do the same thing. So let's talk about the business of tropospheric versus stratospheric water vapor. Now, just to reiterate, the troposphere is that lowest part of the atmosphere. It's actually about the lowest 11 or 12 kilometers, although the exact height varies from place to place and time to time. And it is the part of the atmosphere where everything that you and I call weather happens. Thunderstorms, tornadoes, cyclones, anticyclones, air masses, all the good stuff that you learned in intro, it pretty much all happens in the troposphere. The top of the troposphere is a height called the tropopause. And above the tropopause, we have a big thick layer of the atmosphere, thick as in a long ways from the bottom to the top, a big thick layer of the atmosphere called the stratosphere. It's not thick as in like thick and gooey or dense or something. I mean, quite to the contrary, the air is very thin up there, but it spans a very large number of kilometers, from about 11 or 12 kilometers at its base to about 50 kilometers at its top. And basically nothing weather happens in the stratosphere. Okay? The main thing that's interesting in the stratosphere, as you might recall from ATS-113, is that's where the ozone layer is and so on. But in terms of like weather, there's no clouds to speak of in the stratosphere. There's not jet streams and things like that. Okay, there's nothing meteorologically interesting really in the stratosphere. But that doesn't mean there's no water vapor and so on there. Let's talk about, well, first let's focus on the troposphere. Let's talk about tropospheric water vapor first. Turns out, that's where basically all of the water vapor in the Earth's atmosphere is. Well, I mean, if you actually add up the total amount of water vapor between the surface of the Earth and the tropopause, so you've got the whole thickness there of the troposphere, you've got 99.999% of the water vapor or something crazy like that. There's virtually none of it up there in the stratosphere. In fact, I love this diagram that I found online. This is just somebody's research. I don't remember where. University of Washington, I believe. And it has 4 little diagrams of how some property changes with respect to height. And the top left one is pressure, and you can see how pressure starts off very high near the surface and gets quite low as you go up. And the second one here up at the top right, that is temperature, and you can see how temperature decreases with respect to height in the troposphere. And then you get up into the stratosphere at a height of about 15 kilometers or something like that, and from there on up the temperature increases with respect to height. I'm not worried about the bottom right figure there. I'm not even entirely sure why he was talking about that in that particular study. But that bottom left figure is fascinating. That bottom left figure shows the water vapor partial pressure. That's basically what we called vapor pressure back in intro. It's just a measure of how much water vapor there is in the air. And you can see that on average the amount of water vapor near the surface is a biggish number. And it decreases as you go up in the atmosphere. And by the time you're about 10 kilometers up, it's basically zero. Basically, there isn't any water vapor in the atmosphere that high up. Now, in practice, we can't see this closely enough to see that actually it's not quite zero. But you can see that basically the heights that are the troposphere, like 10 kilometers and down, that's basically where all the water vapor is, with only a tiny bit occurring above about 10 kilometers. So almost all the water vapor is in the troposphere, but for good reason. The troposphere is where the source of water vapor is, namely evaporation off the surface. Water vapor enters the atmosphere via its process called a source, and the source of water vapor in the troposphere is evaporation off the surface, which is physically far from the tropopause. And it's work to get it up there. And as you lift air, you get cooling and condensation and clouds and precipitation, and the water vapor falls out. It's actually really hard to get water vapor away from the surface up high in the atmosphere. That's why there's so much water vapor near the surface and so little, in the middle troposphere or the upper troposphere. In fact, there really aren't any good meteorological processes that can transport water vapor from the surface up through the tropopause and up into the stratosphere. Maybe a little bit can happen in like the overshooting tops of thunderstorms. Maybe a little bit can happen by a few processes. But by and large, from a natural point of view, the stratosphere should be basically bone dry. there really isn't a way to get that tropospheric water up into the stratosphere. Okay. And in practice, this plays out on a climate change kind of context by talking about that water vapor feedback. That water vapor feedback, with that connection between global temperatures and the amount of water vapor in the atmosphere, I deliberately didn't say where the hell that temperature was. Basically, we were talking about surface temperature or near surface temperature, because that is where the water vapor is that is being stored and providing that radiative feedback that amplifies the original radiative forcing of the anthropogenic greenhouse gases. It's all down there in the bottom. You know, in practice, when we were talking about like temperature changes, so, you know, that are observed due to global warming back in like Module 1, you might remember pretty much all of the temperature change was happening at the surface. In fact, some parts of like the upper troposphere and so on are actually colder. But who cares? There's no water vapor up there anywhere, very little. Oh, so that whole business of the water vapor feedback, we're talking about just the very bottom of the troposphere. That's okay. Okay. That's where there's the most water vapor anyway. Alright. So then that makes me wonder, what is the story about the stratosphere? Why do I have slides that say tropospheric and stratospheric water vapor if there isn't such a thing as stratospheric water vapor? Well, there actually is such a thing as stratospheric water vapor, but our crotchety old man scientist over here is going to say, alright, smart guy, how you plan on getting water vapor up there in the stratosphere? Frankly, I'd love to know how they're measuring it. I mean, it's so little water vapor that's up there. But he's got a point. Where's water vapor going to come from? I mean, there's no lakes in the stratosphere. Nothing up there, or oceans. There's nothing up there to evaporate. Now, we can't get like precipitation up in there where like raindrops could be evaporating. And okay, we did talk about the fact that combustion produces water vapor. I mean, we normally think about carbon dioxide as being what comes out of the tailpipe of a car or the exhaust of a jet engine. But jet engines, a big chunk of what comes out of the engines is water vapor. And much of the cruise time of a jet aircraft is in the stratosphere, or at least might be in the stratosphere depending on how high they're flying. Is that what we're talking about? You know, same with like rockets. When a rocket passes through the stratosphere on its way to space, as it's burning its rocket fuel, one of the main exhausts it makes is water vapor. Is that what we're talking about? Are we going to really say... I'm going to take the crotchety old man's opinion here, again, though that one. Yeah, that doesn't sound like that could possibly be enough. That does not make sense to me, that that's going to be what we're talking about. Maybe that's part of the story, but that can't be the whole thing. And it turns out it's not. That's not even that's barely a small piece of the total amount of water vapor in the stratosphere. The problem comes from methane. Oh, that methane, it sneaks in on us again. Methane, remember, is natural gas. It's CH4, and it's an organic molecule. It doesn't last forever. It's oxidized. Those vicious old oxygen molecules, they come and they tear it apart. Look, there are literally, I wrote gigatons, I bet it, of anthropogenic methane in the atmosphere. I'm sure it's more than gigatons. We add gigatons of methane to the atmosphere every year and so on. Remember all those source processes that we talked about for methane, like landfills and leaky natural gas delivery system and fracking and cattle flatulence and rice paddies and agricultural processes and so on. We add it. And did you notice where all those things are? They're all at the surface. So we add methane to the atmosphere, and frankly, most of it is added to the troposphere. I mean, that's where the source is. That's where we're putting it into the atmosphere. But compared to water vapor, methane is a fairly long-lived molecule in the atmosphere. It will eventually break down. It will eventually oxidize into something else, water vapor included. But that's longer than like on the order of days. And so there's actually plenty of time. Even if the processes that can get methane across the tropopause and up into the stratosphere are fairly slow, methane's got time. It can do it. Water vapor, you know, every time we lift it up towards the tropopause, it just condenses out. That isn't going to happen with methane. Methane doesn't condense out. I don't even know what the like condensation of methane would be and all that kind of stuff. It doesn't happen at the temperatures and pressures we observe on our Earth. So even if like it's merely horrible molecular processes like diffusion that could get the methane across the tropopause, which it's not entirely, although tropopause folds and tropopause gaps and all this stuff are a meteorology thing. We're not going to get into that. The point is, we can get some of that anthropogenic methane up there into the stratosphere. Maybe not tons of it, well, I mean literally tons, of course, but not like a huge fraction of it. Sure, methane's going to mostly be down here near the surface of the Earth because that's where the sources are, and frankly, getting it across the tropopause is hard. But some will. There will be such a thing as stratospheric methane. And frankly, I don't give a damn whether the methane is in the stratosphere or it's in the troposphere. It's eventually going to be oxidized. Oxygen molecules will rip it apart. Now, it turns out that's a whole branch of atmospheric chemistry. I had no idea there were so many different chemical processes. You know, the exact chemical equation as to how methane plus oxygen yields, and then one of the byproducts is water vapor. It turns out there's lots of different processes depending on the physical chemistry of the situation. But somehow, whether it eventually happens, those methane molecules do not last forever. Now, the ones that are torn up in the troposphere, which is, by the way, most of them, because that's where most of the methane is, down here in the troposphere with us, well, okay, some PChem class project tears apart that methane molecule in the presence of oxygen, and now we have water vapor. Who gives a damn in the troposphere? We have more than enough water vapor already from evaporation off oceans and evaporation from irrigation and all those other processes. Yeah, that oxidation is producing a small amount of water vapor, but it's just tiny compared to what's being evaporated off the ocean and so on. We don't care. But in the stratosphere, where it really ought to be basically bone dry, this turns out to be by far the largest source of water vapor. Because up there, again, there's not that much methane up there, but every single methane molecule up there in the stratosphere is eventually going to oxidize into water vapor. And the natural amount of water vapor there is basically zero. So this is a huge increase in the amount of water vapor up there in the stratosphere. So, if the methane that was the chemical precursor to this water vapor, if that methane is anthropogenic in origin, guess what? So is that stratospheric water vapor. We are responsible for that stratospheric water vapor that's up there. Again, it's still pretty dry. Don't get me nuts. It's not. Don't go nuts here. We're not talking like it's humid up there. But it's a non-zero amount of water vapor that's up there. A place that used to have basically no water vapor now has water vapor because of us. And need I remind you that water vapor is a greenhouse gas, right? So we have taken a place who had an optical depth of basically zero for water vapor. Well, the water vapor in the stratosphere had an optical depth of basically zero because there basically wasn't any water vapor up there. And now when long-wave radiation is trying to push through that stratosphere, it is passing through a layer of the atmosphere where water vapor is having a non-zero optical depth. Not all long-wave radiation can just get transmitted through the stratosphere anymore. Some of it is being absorbed and then being re-emitted down towards the surface. We have enhanced the greenhouse effect in the stratosphere by our processes about methane becoming stratospheric water vapor. Is this huge? No, I deliberately put on there small. It's on the order of, actually you saw it in one of the earlier presentations of this module on a slide that had all the different trace gases. It's on the order of like 0.2 of a watt per square meter or something like that, but that's a sizable chunk of the total radiative forcing from all anthropogenic sources. Oh, because remember the total forcing was like 1.4 watts per square meter or something like that. So it's a small forcing, but it's actually a fairly large chunk of the total forcing. And it is positive, it is enhancing the greenhouse effect. Oh man, yet another way we've messed up the atmosphere. Oh well, let's answer a couple questions about stratospheric water vapor before we are done with this lecture. Question 4. Nearly all the water vapor in the atmosphere is in the A. Troposphere, B. Stratosphere, C. Mesosphere, D. Cryosphere. Read the question closely, it's actually a little trickier than it might seem, and get a little feedback before you move on to question 5.